When we talk about solving systems of equations, usually we're referring to lines intersecting, and so there's one solution. When we talk about nonlinear systems, as we do in section 3.5, we're going to have parabolas, circles, things that are not lines intersecting with lines, or maybe intersecting with each other. So as you can see in these examples, it's possible to have a line and a parabola intersect twice, or once, or not at all. So we can have different types of solutions. Here are a few more examples where instead of lines intersecting, we have parabolas intersecting with one another. And again, you can see there's examples of two solutions, one solution, or even no solutions. And just one more quick illustration. Check out these parabolas intersecting with circles. You can see 2, 4, 3. You can imagine where there might be one solution or even no solutions. Our first example asks us to solve a nonlinear system by graphing. You can see that we have a parabola in standard form and we have a line in slope-intercept form. And we could remind ourselves about amplitude and y-intercept. We could talk about how to find the axis of symmetry and the vertex. I'm going to hold off on that and just encourage you to use graphing technology. We can see that we have an upside down parabola because the amplitude is negative. We also have a line with a negative slope for the same reason. And you can see that these things are intersecting at -6, 1 and -3, 8. We can go ahead and we can try to check our work to see if this is accurate. If we take our first equation and plug in a -6 wherever we see x, -3 times 36 is -108. -30 times -6 is +180, minus 71. When we blend those together, we come up with 1. So when we plug in -6, out comes 1. We could check with the second equation. When we plug in -6, we'll get +18 minus 17 equals 1. And so -6, 1 is in fact one of our points. The second point of intersection seems to be at -3, 8. And so if we want to check those, wherever we see the x, again, we can insert the -3. -3 squared is 9. 9 times -3 is -27. -30 times -3 is +90, and then minus 71. -27 plus 90 minus 71 is equal to -8. And for the line, when we plug in -3, we're going to get 9 minus 17. We'll come up with -8 again. So -3, -8 is a point on our graph. We're using the graphing technology to produce these parabolas and lines, and then we're just confirming the results by plugging in our values. Here's a second example. This time around we have two parabolas. Notice that one is in a vertex form and the second is in standard form. And if we graph those, we'll come to two parabolas that are intersecting, one along the x-axis and the other on the y-axis. We can go and check again. If we take both equations and plug in 0, wherever we see x, 0 plus 2 is 2, 2 squared is 4, and 4 times a half is 2. So when we plug in 0 into our first equation, out comes 2. For the second equation, 0 squared is 0, 0 times -1/2 is still 0, plus 2 gets us to 2. So 0, 2 is in fact a point on our graph. And we can also check our second point. If we plug in the -2 for x, for our first equation, inside the parentheses, -2 plus 2 is 0, 0 squared is 0, and 0 times a half is still 0. So -2, 0. For our line, that's blue, if we plug in the -2 and square it, we'll get 4. -1/2 times 4 is -2, and -2 plus 2 is 0. So our second point is -2, 0. We can see it from the graph. We can confirm it by plugging in those values. The greater challenge for us is to solve nonlinear systems when we don't have the graphing technology. When we don't have a graphing calculator or Desmos at our disposal, we can use substitution or elimination, and example 2 asks us to use substitution. Notice that we have a parabola that's written out in red. We know that because there's an x squared, and the blue equation only has x to the first, so we're looking at a line. To use substitution, we want to be able to isolate one of those variables, and because the y is only written once in either of those equations, I'd recommend that we try to solve for y. Meaning, let's take that second equation in blue, and if we move the 2x over to the right, we'll get y equals negative 2x plus 7. Now that allows us to take that information and substitute it into the first equation. So we already have the x squared plus 2x. We already have the 5 on the right. Remember, we're subtracting, and we're going to plug that negative 2x plus 7 in. We're going to collect all of our like terms in step 3 and bring everything over to one side of the equation so that we'll have a trinomial. We already have the x squared. 2x minus a negative 2x gives us 4x. We're subtracting the 7, so that gives us negative 7, and when we bring the 5 from the right over to the left, it's going to give us negative 12. So we have that trinomial down at the bottom in step 3. In step 4, we're going to try to factor. We know when we set up our parentheses, we'll have x and x at the front ends. And because we're multiplying to get a negative 12, our signs are going to have to be different. That means we're going to multiply to get negative 12 and add to get 4, which is going to feel a little bit more like subtraction since the signs are different. We can check out our possibilities, 12 and 1, 4 and 3, but 6 and 2 are the ones that are going to properly get us to 12 when we multiply and 4 when we add, assuming that those signs are different. So x plus 6 and x minus 2. If we want to solve for x, then either x plus 6 equals 0, in that case x could be negative 6, or x minus 2 equals 0, so x could equal 2. Just go back and plug either one of those values in wherever you see x. If we take the 2, for example, 2 plus 6 is 8, and 2 minus 2 is 0. 8 times 0 is 0. To go back and figure out what y is, we now need to substitute those values in wherever we see x. So I'm going to take that second equation. Remember, we said that y equals negative 2x plus 7. If we plug the negative 6 in, we're going to get negative 2 times negative 6 is 12, and 12 plus 7 is 19. If we plug in the 2, negative 2 times 2 is negative 4, and negative 4 plus 7 is 3. So it feels like negative 6, 19 is a point on our graph, and 2, 3 is as well. These are our points of intersection, which are our solutions for this system. To check our work, we can take that first equation, and wherever we see x, we can plug in negative 6. Wherever we see y, we can plug in 19. And we can work that out. Negative 6 squared is 36. 2 times negative 6 is negative 12. And we're still subtracting 19. 36 minus 12 is 24. And 24 minus 19 is 5. So we get 5 equals 5. So the equation works, it's true. And that 5, remember, is the right-hand side of that first equation. If we do the same work for our second point, wherever we see x, we plug in a 2. Wherever we see y, we plug in the 3. 2 squared is 4. 2 times 2 is 4. And we're still subtracting the 3. So 4 plus 4 is 8. 8 minus 3 is 5. So again, we come to a true equation. It works. And again, they're referencing that 5. We're not asked to graph this, but we can see the parabola and the line intersecting at negative 6, 19, and at 2, 3. We can also solve by elimination. Elimination works well when we have two equations written one on top of one another where the coefficients of one of our variables are opposites so that when we add together, they drop out. If you remember in section 3.2, we were talking about additive inverses. This is essentially the same thing. If you notice in step 1, if we add the equations, the negative y and the positive y will drop out. Just to try to line things up nicely, I put in a plus 0x. And when we add those things together, 2x squared and 1x squared should give us 3x squared. 4x and 0x should give us 4x. The y's drop out. That's the whole point of doing elimination. And negative 2 and positive 2 equals 0. Just because that right side drops out does not mean we therefore lose the equation. It just means that the left side equals 0. Now our goal is to be able to solve for x, and we've got this binomial on the left-hand side, 3x squared plus 4x equals 0. If you notice that both terms have an x, factor it out, and what's left over is 3x plus 4. The zero product property tells us that when we multiply things together and get 0 as an answer, one of our values there needed to be 0 to begin with. So it's possible that x equals 0, or it's possible that 3x plus 4 equals 0. Therefore, in step 4, when we want to solve for x, if we're saying x equals 0, then that end of it is essentially already done. On the other hand, in the green, 3x plus 4 equals 0. If we subtract the 4 to the other side, it becomes negative, and if we divide by 3, we'll get that the other possibility is that x could equal negative 4/3. So what we're looking for are points of intersection. Points of intersection have x and y values. So I want to take that second equation that was written in blue and rewrite it as y equals negative x squared plus 2, because that allows me to plug in my 0 for x. 0 squared is still 0. The opposite is still 0 plus 2. I should get a 2 out. So 0, 2 should be a point of intersection. If we take the negative 4/3 and square it, we're going to get a positive 16/9. But then remember there's a negative on the outside, so that becomes negative 16/9. If we want to add that to 2, I want to find the common denominator, so I convert that over to 18/9, and I come up with a positive 2/9. So when we plug in negative 4/3, out comes 2/9, and so we have a really nice point of intersection with integer values 0, 2, and we have another nice point. It just is rational values, negative 4/3, comma, positive 2/9. Let's take a moment to check our work. We're suggesting that 0, 2 is a point of intersection. So if we take our first equation and plug in 0 for x and 2 for y, and perform the operations here, 0 squared is 0 times 2 is still 0. 4 times 0 is 0, minus 2. 0 plus 0 minus 2 is negative 2. So negative 2 equals negative 2. That works. That's suggesting that when we plug in 0 and 2 for y, our equation holds, so 0, 2 is a point of intersection. If we take the same original equation and now take our second values for x and y, negative 4/3 and positive 2/9, we've got to perform our order of operations here. It's a little bit tricky because of the fractions, but negative 4/3 squared is 16/9, and negative 4/3 times 4 was going to get us to a minus 16/3. To get to our next step, if we distribute the 2 or multiply the 2 into the parentheses, we're going to get 32/9. If we convert 16/3 into 9ths, we'll get minus 48/9, and we still have the 2/9. We can take negative 16/9, that comes from 32 minus 48, so negative 16/9 minus 2/9. That's going to get us to negative 18/9, which reduces to negative 2. So although the fractions were not as easy to deal with as the integers, it still works, and it tells us that these two parabolas intersect twice, once at the point 0, 2, right on the y-axis, and also at -4/3 and 2/9. And finally, I'd like to double back to the previous problem, example 2, and we did substitution. We had x squared plus 2x minus y equals 5 and 2x plus y equals 7. And we found the points of intersection to be -6, 19, and 2, 3. I want to do that with elimination because I also noticed that we have a negative y and a positive y sitting there. So in step 1, if we align those and add, we should get to x squared plus 4x equals 12. And then again, if we bring the 12 to the left-hand side, we get this nice trinomial. And that factors just like we did in the when we got the substitution. We get to x plus 6 and x minus 2, which tells us that x could either equal 6 or -6 or +2. And then when we go to plug both of those into one of our equations, if we rewrite the second equation as y equals -2x plus 7 and plug in a -6, we're going to get 12 plus 7, and that's going to give us 19. So that confirms -6, 19 is a point on our graph. And also if we plug in 2, we're going to get -2 times 2, that's -4. -4 plus 7 is 3, and so 2, 3 is also a point on our graph. So substitution and elimination are really two ways to describe the same process. We're trying to get from two equations and two unknowns down to one equation and one unknown so that we can then solve. We're working now with nonlinear, so there's more than one possible answer at times, but both of those methods are very much analogous to when we were doing it with linear equations.